The global push toward clean energy has placed green hydrogen at the center of discussions about how to decarbonize heavy industries, transportation, and power generation. Unlike hydrogen produced from fossil fuels like the gray or blue hydrogen, green hydrogen is generated using renewable electricity and water through a process called electrolysis, splitting water molecules into hydrogen and oxygen. However, despite its environmental promise, green hydrogen production faces three major hurdles: high material costs, equipment durability in harsh conditions, and limited scalability. These challenges have made large-scale deployment slow and expensive, especially in coastal areas where seawater is abundant but corrosive. A team at the University of Hong Kong may have found a solution. They've developed a new type of stainless steel material called SSH2 that could overcome these technical and economic barriers. This innovative material not only resists corrosion from seawater, but also cuts costs drastically and is ready for industrial production. In this video, we'll take a closer look at how SSH2 works, why it's such a critical innovation, and how it could change the global hydrogen economy. We'll also examine who stands to benefit the most and what the long-term implications might be for energy markets and climate goals. Producing green hydrogen at scale requires durable and expensive electrolyzer machines that split water into hydrogen and oxygen using electricity. The key components of these systems, especially the electrodes, must withstand highly corrosive environments, particularly when seawater is used instead of purified water. Currently, to prevent corrosion, manufacturers use expensive materials like titanium, often coated with rare and costly metals such as platinum or gold. This dramatically increases the price of electrolyzers, making large-scale projects financially challenging. Additionally, because traditional materials can't withstand direct exposure to seawater, many systems rely on energy-intensive desalination processes to purify water before electrolysis. This adds complexity, cost, and energy consumption, which is counterproductive for a technology aiming to be truly green. One of the most remarkable features of this stainless steel material is its resistance to corrosion in chloride-rich environments, such as seawater. The HKU team achieved this through a process called sequential dual passivation, which involves forming two protective oxide layers, one of chromium oxide, the other of manganese oxide. This dual-layer structure provides unprecedented stability, enabling the material to operate at up to 1700 millivolts in corrosive seawater without degrading. For comparison, many conventional stainless steels begin to corrode at much lower voltages in similar conditions. This resistance opens the door for direct seawater electrolysis, a game-changing advancement that eliminates the need for desalination. By cutting out this costly and energy-intensive step, SSH2 not only makes the process more sustainable, but also much more affordable. Material costs have always been a major barrier to scaling up green hydrogen infrastructure. By replacing titanium and precious metal coatings with this stainless steel material, the cost can drop by up to 40 times. For example, a 10 megawatt proton exchange membrane electrolyzer, a common type used in green hydrogen production, might cost $17.8 million Hong Kong dollars or around $2.75 million US dollars using traditional materials. This massive cost reduction could transform the economics of green hydrogen, making it financially viable for countries and companies that previously found the technology too expensive to adopt. Another strength is its durability under extreme conditions. Electrolyzers operating in marine or coastal settings are exposed to harsh, corrosive elements for years. Equipment failure or frequent maintenance disrupts operations and drives up costs. SSH2 addresses this by significantly extending the lifespan of electrolyzer components. It requires less maintenance and can withstand long-term exposure to seawater without significant wear. Importantly, it's not just a lab-scale innovation. HKU researchers have already produced tons of this wire in collaboration with a manufacturing facility in mainland China, demonstrating that the material can be manufactured at an industrial scale. This positions it for immediate adoption in commercial hydrogen projects. HKU's collaboration with factories in mainland China reflects the country's strategic investment in green hydrogen as a pillar of its long-term energy and industrial policy. China is already a global leader in renewable energy deployment, and SSH2 will strengthen its position in the hydrogen economy. By combining manufacturing scale, research expertise, and policy incentives, China is well positioned to deploy this stainless steel material in domestic and international hydrogen projects. Major energy companies like Shell, Linde, and Bloom Energy are aggressively expanding into green hydrogen. These firms have the infrastructure and capital to scale up production quickly. Integrating SSH2 into their supply chains could help them reduce project costs, improve reliability, and accelerate rollout. Countries with abundant and inexpensive renewable energy, such as Australia, the United States, and regions in the Middle East, are ideal candidates for green hydrogen production. These nations can leverage SSH2 to build cost-effective electrolyzers and produce hydrogen at competitive prices, estimated between 3 to 5 euros per kilogram, which is approaching parity with fossil fuels. To understand its economic potential, it's helpful to compare the cost of green hydrogen with conventional fuels. As of 2024, green hydrogen costs between $1 and $1.80 per kilogram, which is roughly equivalent to $3.30 to $5.94 per gallon of gasoline in terms of energy. In comparison, the average price of gasoline in the US, as of when this video is made, is around $3.19 per gallon, not including the hidden environmental costs, such as pollution and carbon emissions. While green hydrogen is still more expensive on paper, SSH2 could help push it toward the lower end of the price range. Combine this with falling renewable energy costs, and hydrogen could soon become a cheaper, cleaner alternative to gasoline, especially when factoring in the hidden environmental and health costs of fossil fuels. SSH2's impact could extend far beyond individual projects. By removing key technical and economic roadblocks, it may accelerate the global timeline for making green hydrogen a mainstream energy source. This stainless steel material could help meet this milestone even sooner by lowering capital and operational costs for electrolyzer systems. In the long term, green hydrogen enabled by innovations like SSH2 could become essential for decarbonizing heavy industry, shipping, aviation, ammonia production, and steel making. These sectors are some of the hardest to electrify, and hydrogen offers a realistic path to cutting their carbon emissions. In conclusion, the invention of SSH2 stainless steel by the University of Hong Kong marks a turning point in clean energy technology. By solving critical challenges in cost, corrosion, and scalability, this material opens the door to widespread, affordable green hydrogen production, especially in seawater-rich regions where traditional electrolyzers fall short. As nations race to decarbonize and global energy markets shift away from fossil fuels, SSH2 offers a powerful tool to speed up that transition. Its combination of technical resilience and cost efficiency makes it one of the most promising innovations in the clean energy space today. If adopted widely by energy companies, manufacturers, and governments, SSH2 could become the cornerstone of a hydrogen-powered future, delivering clean, scalable, and sustainable energy to meet the world's growing demands. Before you go, check out some of my other videos. Don't forget to hit that like button and subscribe. Thanks for watching. We'll see you at the next one.